The sand here looks empty at first glance, a pale and uneven plain stretching across the seafloor like a forgotten runway. No coral towers rise from it, no rocks offer shelter, no obvious movement breaks the stillness. This is the kind of environment predators love and prey fear, a place where there is nowhere to hide and nowhere to anchor your eyes. The water above is hazy with suspended silt, sunlight diffused into a dull glow that flattens shapes and erases depth. In ecosystems like this, survival usually belongs to the fast, the armored, or the venomous. And yet, somewhere in this exposed nothingness, something is watching, not hiding, waiting. A ripple moves across the sand, barely noticeable, like a shadow cast by a passing cloud. Then another. The sand itself seems to breathe, and what looked like emptiness begins to rearrange into form. Arms unfold, then flatten, then pull back again, their edges rippling with deliberate control. This is not camouflage in the traditional sense. There is no attempt to blend into the background, no passive disappearance. What emerges instead is performance, identity as a weapon. This is the mimic octopus, an animal that does not merely avoid detection, but actively manipulates perception itself. Mimicry works because most animals do not have the luxury of careful analysis. In the wild, hesitation kills. A predator approaching potential prey has only moments to decide whether the encounter is worth the risk. One wrong calculation, one bite taken from the wrong body, can mean paralysis, envenomation, or death. Evolution has shaped countless species to exploit this hesitation, wearing warning colors, exaggerated shapes, or aggressive postures that advertise danger, even when none exists. The mimic octopus takes this evolutionary shortcut and pushes it to an extreme, borrowing the reputations of multiple animals and deploying them as needed, sometimes within seconds, sometimes mid-movement, sometimes while already being watched. What makes this possible is not illusion, but anatomy. The octopus body is a masterclass in flexibility, built without rigid bones and powered by muscles that can operate independently along each arm. Every arm can stiffen, elongate, flatten, or curl with fine control, allowing the animal to sculpt its silhouette moment by moment. Skin texture changes follow just as quickly, with specialized cells that alter color and contrast in response to light and background. This is not random color change. It is coordinated patterning, guided by visual input, neural processing, and learned environmental cues. The result is an animal that does not commit to a single form, but instead treats shape itself as a variable. In the open sand flats where mimic octopuses are most often observed, this ability is not a novelty. It is a necessity. There are few crevices to retreat into and little structural complexity to break up outlines. Predators patrol low and fast across these plains, scanning for movement rather than color, reacting to silhouettes more than detail. For an octopus here, remaining still is not enough. Being invisible is nearly impossible. So instead, the mimic octopus chooses to be visible in the wrong way. When threatened from above, it may draw its arms together and extend them backward in a rigid banded formation, gliding just above the sand. The resemblance to a venomous sea snake is immediate and convincing, especially in low visibility water where fine details blur. The alternating dark and light bands, the sinuous motion, the narrow profile, all trigger avoidance in predators that have learned through experience or instinct that sea snakes are not worth testing. The octopus does not need to be perfect. It only needs to be convincing enough to buy a moment of doubt. And doubt is often enough. At other times, the same animal may spread its arms wide, lifting them upward and outward, exaggerating their length and stiffness until the silhouette becomes spined and imposing. The posture echoes that of venomous lionfish, whose extended fin rays form a floating fence of pain. Predators that have learned to recognize this shape do not need to be reminded twice. The mimic octopus does not carry venom in its arms, but it does not need to. The threat exists entirely in the mind of the observer. Even flatfish enter the performance. By flattening its body and arms against the sand and undulating forward in short bursts, the octopus can resemble a gliding sole or flounder, animals so unremarkable and nutritionally unrewarding that many predators simply ignore them. In this form, The octopus is not advertising danger, but insignificance, presenting itself as something not worth the energy of pursuit. Again, the goal is not deception in a theatrical sense, but decision manipulation. Make the predator choose to look elsewhere. These transformations are not fixed routines triggered automatically by danger. They appear to be context-dependent, adjusted to the type of threat, the angle of approach, and the surrounding conditions. A predator cruising overhead may elicit one response, while a benthic hunter moving along the sand may trigger another. This suggests not just reflex, but assessment, a capacity to evaluate which disguise carries the highest survival value in a given moment. In an environment where mistakes are fatal, this flexibility becomes a form of intelligence expressed through flesh. But mimicry is not used only to avoid death. It is also a hunting strategy. The same disguises that repel predators can be used to disarm prey. On the open flats, prey species are constantly scanning for danger, relying on quick pattern recognition to decide when to flee. A shape that reads as dangerous but slow, or familiar but irrelevant, can slip closer than something obviously predatory. The mimic octopus exploits this blind spot, approaching prey while wearing a borrowed identity that lowers suspicion or delays escape. Crustaceans, small fish, and burrowing animals often hesitate when confronted with what appears to be a known threat with predictable behavior. A sea snake hunts differently than an octopus. A flatfish poses no threat at all. By presenting itself as something else, the octopus disrupts the prey's risk assessment, closing the distance before revealing its true nature. When the strike comes, it is sudden and precise, arms snapping forward to envelop the target in a living net, suction cups locking on before the prey can process the mistake. The silty environment amplifies this effect. Suspended particles reduce contrast and blur edges, turning sharp outlines into suggestions. In such conditions, movement and posture carry more weight than color accuracy. A predator does not need to see every detail of a sea snake to avoid it. The general form is enough. The mimic octopus operates in this perceptual gray zone, where biological shortcuts dominate decision-making. It is not fooling predators into believing a lie. It is encouraging them to follow rules they already use to survive. From an ecological perspective, this places the mimic octopus in a unique niche. It is not the fastest hunter, not the most armored, not the most venomous. Instead, it functions as a behavioral chameleon, inserting itself into the warning systems of the ecosystem and redirecting them for its own benefit. This kind of mimicry has ripple effects. Predators that overreact to false threats may alter hunting patterns, while prey species may become more cautious, raising the overall tension of the environment. In this way, the octopus influences not just individual interactions, but the behavioral landscape of the sandflats themselves. What makes this strategy particularly powerful is its efficiency. Mimicry is energetically cheap compared to speed or armor. It requires control, not muscle mass, neural processing, not physical strength. For an animal with a high metabolic cost and a soft body vulnerable to injury, this trade-off makes evolutionary sense. Instead of evolving thicker skin or stronger toxins, the mimic octopus invests in control, learning, and flexibility. It becomes a problem solver rather than a bruiser. The visual rhythm of these transformations is mesmerizing to watch and devastatingly effective in practice. One moment, the octopus is a loose bundle of arms drifting across the sand. The next, it stiffens into a banded line, then collapses again, then spreads wide, then flattens. Each shift is smooth, purposeful, and immediate. There is no pause between identities, no reset to a neutral state. The animal flows from one form to another as if shape itself were optional, a tool to be selected rather than a constraint to endure. This constant redefinition of self is what makes the mimic octopus so difficult to categorize. It is not a master of disguise in the traditional sense because it does not disappear. It becomes. It inserts false information into the decision-making of other animals, rewriting the rules of engagement on the fly. In a habitat defined by exposure and risk, this ability turns vulnerability into leverage. And perhaps most unsettling of all is how deliberate it feels. Watching a mimic octopus at work does not give the impression of instinct alone. There is timing, selection, adjustment. A sense that the animal is not merely reacting, but choosing. In a place where visibility is poor and danger is constant, the most powerful weapon is not venom or speed, but the ability to control what others think they see. At first glance, the water looks almost theatrical, too clean, too evenly lit, as if the reef has been staged for observation rather than lived in. Sunlight filters down in broad, pale shafts, scattering across open sand and low coral rubble, illuminating everything without favor. There are few hiding places here, and no deep shadows to retreat into. This is not the kind of environment that rewards brute force or reckless speed. It rewards control. Somewhere within this open brightness, something is already preparing an attack, though nothing about the scene yet suggests urgency. The water remains calm, the sand undisturbed, and then the background itself begins to move. The cuttlefish does not arrive like a predator. It emerges like a thought forming, its body hovering just above the seabed, arms relaxed, posture unthreatening. Its skin carries soft purples and pale whites that ripple gently, not in reaction to danger, but as if testing the space around it. There is no rush, no tension in its movement. If anything, it appears contemplative, drifting with the confidence of an animal that knows it has time. This calm is deceptive. The cuttlefish is already working, already calculating, already shaping the encounter long before prey realizes it has been noticed. For the cuttlefish, skin is not decoration. It is not even camouflage in the simple sense of hiding. It is a weapon system layered directly onto the body, capable of altering color, contrast, texture, and motion with astonishing speed. Specialized cells embedded in the skin expand and contract under neural control, exposing pigments or reflective layers beneath. But color alone is only part of the story. The skin can raise small, muscular bumps, changing its texture to mimic sand, coral, or rock. At the same time, moving patterns sweep across the body in waves, pulses, or flickers, each serving a specific purpose depending on context. This is not random display. It is targeted manipulation of perception. In open water, depth and distance are difficult to judge even for human eyes. For fish and crustaceans, whose survival depends on split-second timing, these judgments are everything. A predator that appears farther away than it is, or moving slower than it truly is, gains a lethal advantage. The cuttlefish exploits this weakness by projecting patterns that interfere with motion detection itself. Bands of light and dark slide across its body in opposing directions, creating false cues about speed and orientation. To prey, the cuttlefish seems to drift when it is actually closing in, or to expand when it is not moving at all. The effect is not hypnosis in any mystical sense. It is sensory overload, a deliberate scrambling of visual processing that delays reaction by fractions of a second. In hunting, fractions of a second decide outcomes. As the cuttlefish advances, its body remains low and steady, fins undulating smoothly along its sides to maintain position without stirring the sand. It does not chase. It stalks. Each movement is measured, calibrated to avoid triggering the prey's escape threshold. Small fish hover nearby, their attention divided between scanning for threats and feeding along the bottom. A shrimp creeps across the sand, antennae sweeping, unaware that the background behind it is actively reshaping itself to close the distance. The cuttlefish's intelligence becomes apparent here, not through problem-solving puzzles or tool use, but through environmental choice. It positions itself against backgrounds that amplify its patterns rather than obscure them. Bright sand reflects light, making contrast shifts more dramatic. Patchy coral rubble breaks up outlines, allowing pattern motion to bleed into the environment. This is not automatic. Observations show that cuttlefish actively choose hunting grounds that suit their visual strategy, selecting locations where their skin displays will have maximum effect. In doing so, they are not merely reacting to the environment, they are using it. As the distance narrows, the cuttlefish's body language remains eerily relaxed. There is no coiling of muscles, no obvious preparation for attack. Its arms hang loosely, suckers inactive, tentacles hidden and compact. To an outside observer, it appears almost indifferent to the prey drifting within reach. This is the final deception. The cuttlefish does not telegraph its strike. It denies the prey any visual cue that would prompt escape. Then, without warning, the calm breaks. Two specialized feeding tentacles shoot forward with explosive speed, extending farther than the body length in a blink. The motion is so fast it creates a visible blur, a sudden eruption from stillness. The tentacle tips strike the prey with precision, adhesive pads snapping shut as they make contact. Before the prey can register what has happened, it is yanked backward toward the cuttlefish's arms, enveloped, subdued. The entire sequence takes less time than a startled fish would need to flick its tail. This contrast between serenity and violence is what makes cuttlefish hunting so unsettling. There is no chase, no visible escalation. One moment the animal appears almost decorative, its skin shimmering softly in the light. The next, the encounter is over. This economy of movement reflects a broader strategy. The cuttlefish minimizes energy expenditure and risk, relying on sensory dominance rather than physical struggle. In an ecosystem filled with sharp spines, venom, and fast predators, avoiding injury is as important as securing food. The patterns that precede the strike often intensify just before the attack, though not in ways prey can easily interpret. Subtle shifts in brightness and contrast sweep across the body, further confusing motion detection. For prey already struggling to judge distance, this last burst of visual noise disrupts timing completely. Escape responses trigger too late or in the wrong direction. The cuttlefish does not need to be faster than its prey in absolute terms. It only needs to act when the prey's perception is compromised. What elevates this strategy beyond instinct is the cuttlefish's ability to adjust it based on context. In different lighting conditions, pattern speed and contrast change. Against darker backgrounds, displays become more subdued, prioritizing texture over brightness. Against bright sand, patterns grow bolder, leveraging reflected light to amplify the illusion. This flexibility suggests ongoing assessment rather than fixed behavior, a level of cognitive involvement that blurs the line between reflex and decision. Cuttlefish are known to possess some of the most developed nervous systems among invertebrates, with large brains relative to body size and complex neural pathways dedicated to vision and motor control. Their eyes, capable of detecting polarized light, provide information invisible to many other animals, revealing contrast and texture details that guide both camouflage and display. This sensory richness feeds directly into their hunting strategy, allowing fine-tuned control over how they appear from multiple angles. In effect, the cuttlefish is not just seeing the environment, it is seeing how the environment sees it. The mood this creates is one of quiet menace. Unlike predators that advertise strength through size or aggression, the cuttlefish radiates composure. Its confidence lies in preparation, in the knowledge that by the time prey senses danger, it is already too late. There is a subtle irony here. An animal so visually dynamic, capable of dramatic color, shifts and flashing displays, chooses to move through its world with restraint. It does not flaunt its power. It conceals it beneath calm. After the strike, the patterns fade, the skin settling back into softer tones as the cuttlefish feeds. There is no celebration, no display of dominance. The environment returns to stillness, as if nothing has happened. Nearby fish resume their movements, unaware that the same calm shape drifting above the sand could turn lethal again without warning. The cuttlefish drifts on, already scanning, already adjusting its skin to the next background, the next opportunity. In ecological terms, this places the cuttlefish in a unique role. It is both predator and illusionist, shaping interactions not through force, but through misdirection. Its hunting success depends as much on the visual processing limitations of other animals as on its own speed or strength. This creates a subtle arms race, where prey species evolve sharper detection thresholds, while the cuttlefish refines its patterns in response. The battlefield is not physical space alone, but perception itself. Watching a cuttlefish hunt forces a reconsideration of what a weapon can be. Here, lethality is woven into skin, into light, into movement. The animal's most dangerous feature is not hidden in its mouth or claws, but spread across its body for all to see, misunderstood until the final moment. In bright blue water, beneath the calm surface of an open reef, the cuttlefish demonstrates that control over attention can be as deadly as any fang or spine. The open ocean offers no forgiveness. There are no walls to press against, no sand to melt into, no coral branches to hide behind. Space stretches in every direction, a three-dimensional void where movement is visible from far away and hesitation is punished instantly. In this environment, survival does not belong to the best hider alone. It belongs to the animal that can vanish through motion, rewrite trajectories mid-chase, and turn empty water into a trap. This is where squid dominate, not by blending into the background, but by mastering speed, misdirection, and controlled chaos. A squid does not enter a scene so much as erupt into it. One moment the water appears empty, broken only by drifting particles and distant light. The next, a long, torpedo-shaped body streaks through the frame, fins flaring, mantle pulsing, tentacles trailing like drawn blades. Squid are not subtle by accident. They are built for rapid engagement, animals whose bodies are designed around acceleration rather than concealment. Yet even here, appearance deceives. Speed is only part of the strategy. Direction, timing, and perception matter just as much. The defining engine of squid movement lies within the mantle, a muscular chamber that draws water in and expels it forcefully through a narrow siphon. This jet propulsion allows squid to accelerate almost instantly, launching themselves forward with explosive bursts that few predators can match. More importantly, the siphon is mobile. By rotating it, the squid can redirect thrust in fractions of a second, changing direction without slowing down. What appears to be reckless speed is actually controlled maneuvering, a constant recalculation of vectors that lets the squid zig, cut, and reverse course in ways that break pursuit patterns. In open water, predators rely on prediction. They anticipate where prey will be based on its current trajectory and speed. Squid exploit this dependence by refusing to behave predictably. A burst forward becomes a sudden stop. A straight line turns into a vertical drop. A retreat flips into a charge. These abrupt shifts are not random. They are timed to the predator's approach, executed when commitment is highest and correction is hardest. The result is not just escape, but confusion, a disruption of the predator's internal tracking system. This mastery of motion extends into how squid hunt. Unlike animals that rely on structure to corner prey, squid turn the open ocean itself into an ambush zone. They patrol mid-water, hovering just within visibility, bodies angled slightly upward, eyes scanning for contrast rather than shape. When a fish passes within range, the attack unfolds in layers, each specialized limb performing a different role. Squid arms and tentacles are often mistaken as the same, but their functions are distinct. The arms are shorter, lined with suckers along their length, and built for grip and manipulation. The tentacles are longer, retractable, and end in expanded clubs packed with suckers designed for initial contact. During a strike, the tentacles fire first, shooting forward like elastic spears. They latch onto the prey in an instant, after which the arms pull it inward, securing and positioning it for feeding. This division of labor allows the squid to attack from a distance while minimizing exposure, a critical advantage in open water where closing space too slowly invites counterattack. The speed of this sequence is difficult to appreciate until seen in real time. Tentacles extend and retract faster than most prey can react, transforming empty space into a lethal reach zone. What looks like a miss from one angle becomes a perfect capture from another, as the tentacle clubs curve inward mid-extension, compensating for prey movement. This is not brute force. It is precision under pressure. The product of nervous systems evolved to coordinate rapid movement across flexible limbs without rigid support. Camouflage still plays a role, but not in the traditional sense of hiding. Squid skin contains chromatophores capable of rapid color change, similar to cuttlefish, yet squid often use this ability differently. In shallow waters, where sunlight creates glare and reflections, squid exploit brightness rather than darkness. By flashing pale tones or reflective patterns, they blend into surface glare, becoming difficult to track against shimmering backgrounds. Their bodies mirror light conditions, turning brightness into cover. In these environments, being invisible does not mean being dark. It means being unreadable. In deeper waters, where light fades and contrast dominates, squid reverse the strategy. Darkness becomes concealment. Their bodies darken, outlines soften, and bioluminescent organs in some species break up silhouettes by emitting faint counter-illumination. This erases the shadow that would otherwise betray them when viewed from below. Here, stealth is not about stillness, but about alignment with the ambient light field, matching not the background, but the absence of light itself. Defense, for squid, is never singular. When escape through speed fails or surprise becomes unavoidable, misdirection takes over. The inking response is often imagined as a simple cloud meant to obscure vision. But in many squid species, ink is deployed with intention and structure. Rather than dispersing randomly, the ink can be released as dense, cohesive masses that hold shape briefly in the water. These pseudoforms act as decoys, occupying the predator's attention while the squid jets away in a different direction. To a pursuing predator, the decoy looks like the squid it was chasing, complete with similar size and density. In the confusion of motion and turbulence, this momentary illusion can be enough to redirect the attack, buying the squid critical distance. The ink itself may also carry chemical irritants that overload sensory systems, adding another layer of disruption. Again, the goal is not concealment alone, but decision interference. This emphasis on misdirection reflects the squid's ecological reality. Many squid species are prey as often as they are predators, occupying a middle tier in marine food webs. They are hunted by fish, marine mammals, and even birds, while simultaneously hunting smaller fish and invertebrates. To survive in this role, they must be capable of both offense and defense, without specialization that locks them into one strategy. Speed allows escape. Tentacles allow capture. Ink allows reset. Each tool compensates for the absence of hard armor or venom. The visual impression of a squid in motion reinforces this duality. Its body appears streamlined and vulnerable, fins fluttering gently when calm, yet capable of transforming into a projectile without warning. The tentacles, normally hidden among the arms, launch forward suddenly, changing the animal's profile from passive to aggressive in a heartbeat. This transformation is startling not because it is violent, but because it is so clean, so efficient, so brief. Ecologically, squid reshape open water dynamics by compressing time. Encounters that might stretch into prolonged chases with other predators resolve almost instantly with squid. This alters prey behavior, favoring vigilance and schooling, and influences predator tactics, rewarding ambush and surprise. Squid become moving hotspots of energy transfer, converting plankton-fed fish into biomass accessible to larger predators, linking trophic levels through rapid turnover. Their sensitivity to environmental conditions further underscores their role as indicators of ecosystem health. Squid metabolism responds quickly to temperature changes, influencing growth rates, migration patterns, and population booms or crashes. In warming waters, squid populations can expand rapidly, capitalizing on their fast life cycles and flexible behavior. This adaptability, rooted in speed and sensory acuity, allows them to exploit shifting conditions faster than many competitors. Yet adaptability comes at a cost. High energy demands require constant feeding. A squid that fails to capture prey cannot simply wait it out behind a rock. It must move, search, engage. This necessity drives the relentless precision of its hunting style, the constant scanning, the readiness to fire tentacles at a moment's notice. Every successful capture is not just a meal, but fuel for the next burst of survival. When seen in silhouette against the blue gradient of open water, a squid looks almost unreal. Its elongated body tapers into fins that ripple like wings. Its eyes, large and forward-facing, fix on targets with unsettling focus. And when the strike comes, tentacles explode forward, straight and rigid, transforming the animal into a living projectile launcher. The open ocean, empty and vast, suddenly feels constrained, as if space itself has folded inward around the prey. Squid demonstrate that camouflage alone is not enough in a world without walls. Speed must be paired with control. Power must be paired with misdirection. And survival must be earned through constant engagement with space, light, and motion. In turning the open ocean into an ambush zone, squid redefine what it means to hunt without cover, proving that even in the most exposed environments, mastery of movement can create shadows where none exist. The surface of the ocean lies. From above, it looks open, bright, almost harmless, a sheet of shifting blue reflecting the sky. Sunlight scatters across ripples, dazzling the eye and flattening depth into illusion. From below, that same surface becomes a ceiling of glare, a blinding sheet where shapes lose definition and movement turns into shadow. This boundary between worlds is where the great white shark prefers to hunt, not because it is chaotic, but because it is predictable. Light behaves the same way every day. Prey behaves the same way every day. And the shark has evolved to exploit both with ruthless efficiency. Far beneath the surface, the water darkens into a gradient of blue that swallows detail. Here, a massive body moves with deceptive calm. The shark does not thrash or rush. Its tail sweeps side to side in slow, economical arcs, conserving energy, maintaining position. From this depth, it is nearly invisible. Countershading cloaks its form, a dark back blending into the abyss below, a pale belly dissolving into the brightness above. To anything swimming at the surface, there is nothing beneath them but open water. That assumption is fatal. The great white's most effective weapon is not its teeth, but its angle of approach. By rising from below, it turns the physics of light into camouflage. Seals and sea lions silhouetted against the sky cannot easily detect movement beneath them. Their eyes are adapted for horizontal scanning and surface threats, not for discerning subtle shifts in brightness below a glare-filled ceiling. The shark uses this blind zone deliberately, timing its ascent so that its final burst occurs only when escape is already impossible. This strategy reveals something fundamental about the great white's hunting philosophy. It is not a reckless attacker. It is an ambush predator that relies on precision, surprise, and calculation. Every successful strike begins long before the breach, triggered not by sudden aggression, but by information gathering. The hunt often starts with scent. A great white's olfactory system is exquisitely sensitive, capable of detecting trace amounts of blood or bodily fluids diluted across vast distances. When these chemical cues drift through the water, they do not trigger an immediate charge. Instead, they initiate investigation. The shark aligns itself with the current, following the gradient of scent toward its source, adjusting course as concentrations rise or fall. This is not blind tracking. It is three-dimensional navigation through invisible signals. As the shark closes in, another sense takes over. Along its body runs the lateral line, a network of sensory organs tuned to pressure changes and vibrations in the water. Every struggling fish, every swimming seal, every splash at the surface produces a unique signature of movement. The shark reads these vibrations like a map, distinguishing between the rhythmic strokes of a healthy swimmer and the erratic patterns of injury or fatigue. This ability allows it to identify potential prey without seeing it, turning murky water and low visibility into an advantage rather than a limitation. These sensory cues guide the shark toward specific hunting zones, places where the odds favor ambush over pursuit, drop-offs where shallow shelves fall suddenly into deep water, murky transitions where clear currents meet sediment-rich runoff, coastal edges where seals gather near the surface, resting, playing, or feeding. These are not random locations. They are ecological choke points where prey behavior becomes predictable and escape routes narrow. The great white positions itself beneath these zones, hovering just deep enough to remain unseen, its body angled upward. From here it waits. Waiting is not passive. It is active monitoring, constant adjustment, subtle repositioning to stay aligned beneath moving prey. The shark does not need to be faster than its target over long distances. It only needs to be faster for a few critical seconds. When the moment comes, the shark accelerates with explosive power. Its body, shaped like a torpedo, is built for bursts rather than endurance. A stiff, crescent-shaped tail delivers immense thrust, propelling the shark upward in a sudden vertical sprint. Muscles along its flank contract in sequence, transferring energy efficiently through the water. This design sacrifices sustained speed for raw acceleration, a trade-off perfectly suited to ambush. The breach itself is the visible end of a much longer process. To the prey, it appears as chaos, a violent eruption from nowhere. To the shark, it is the culmination of positioning, sensing, and timing. In many cases, the first contact is not meant to kill outright. This is where the concept of the test bite emerges, often misunderstood as mindless aggression. A test bite is information gathering at close range. The shark uses its teeth and jaws to assess unfamiliar objects, determining texture, fat content, resistance, and identity. Unlike seals, humans are not part of the great white's natural prey profile. When a shark encounters something unexpected at the surface, a single bite can provide crucial data. Fatty tissue, blubber thickness, movement patterns, all register immediately. If the object does not match expected prey characteristics, the shark often disengages rather than continuing the attack. This behavior reflects caution rather than rage. Great whites cannot afford unnecessary injury. A damaged jaw, broken tooth, or infected wound can be fatal over time. Every bite carries risk. The test bite allows the shark to minimize that risk by quickly evaluating whether the target is worth the energy and danger of a full commitment. In an environment where meals are spaced far apart, efficiency matters. When the target is a seal or sea lion, the calculation changes. These animals are energy-dense, rich in fat, and worth the effort. A powerful initial strike can incapacitate them immediately, either through massive trauma or by dragging them below the surface where drowning becomes inevitable. The shark may then release the prey, allowing it to weaken before returning to feed. This tactic reduces struggle and lowers the chance of injury during consumption. From an evolutionary perspective, this behavior highlights the great white's role as a selective predator rather than a constant killer. It does not hunt indiscriminately. It targets individuals and situations that offer the highest return for the lowest risk. This selectivity shapes prey populations, favoring vigilance, group cohesion, and the avoidance of risky behaviors near surface edges. The shark's physical design reinforces this approach. Its rigid fins provide stability during sudden acceleration, while its streamlined body minimizes drag during vertical ascent. The jaw structure, equipped with serrated teeth, is optimized for slicing through thick blubber rather than gripping or chewing. Each feature reflects a predator evolved to strike hard, assess quickly, and disengage if conditions are unfavorable. Even the shark's apparent stillness between hunts is deceptive. Maintaining position in the water column requires constant micro-adjustments, subtle tail movements, and fin corrections. The shark is always working, always balancing energy expenditure against opportunity. This constant calculation is invisible to casual observation, but it defines the animal's existence. The great white's presence also reshapes entire ecosystems. Its hunting pressure influences where seals choose to rest, how they enter and exit the water, and how long they linger near the surface. This creates cascading effects, altering nutrient distribution, prey movement patterns, and even coastal behavior. The shark is not just a predator. It is an ecological force, shaping behavior through fear as much as through consumption. The image of the great white as a mindless killing machine collapses under closer examination. What emerges instead is a highly specialized hunter that relies on sensory integration, environmental awareness, and precise biomechanics. Its power is undeniable, but it is wielded with restraint. The violence it delivers is brief, purposeful, and calculated. Visually, the moment of attack remains unforgettable. A dark shape rising through a column of blue brightness, accelerating toward the surface with terrifying speed. The contrast between shadow and light collapses as the shark breaks into the glare, transforming invisibility into impact. It is a reminder that in the ocean, danger often comes not from what you see, but from what you cannot. The great white shark does not dominate the sea by chasing everything it encounters. It dominates by understanding edges, by exploiting sensory blind spots, and by turning the physics of light and motion into weapons. In a world defined by vast open space, it has learned that the most effective place to hunt is not the middle, but the boundary where one world ends and another begins. The blue here never stays still. Light fractures as it passes through surface chop, bending into shifting bands that slide across reef walls, sand channels, and open water alike. Shadows form and dissolve without warning, cast by clouds, waves, and the slow sway of coral heads. In this moving mosaic, shapes are never fixed, and certainty is rare. It is within this instability that the tiger shark thrives, not by overpowering the environment, but by becoming part of its visual noise. Long before its reputation earned fear, its body had already learned how to disappear. From a distance, the tiger shark looks unmistakable, large, solid, confidently cruising through open water. Up close, its defining feature begins to unravel perception. Dark vertical striping runs down its flanks, not as decoration, but as disruption. In static light, the pattern is clear. In moving water, it fragments. As the shark passes through alternating bands of brightness and shadow, its outline breaks apart, stripes aligning with the flicker of surface light and reef shade. What should be a single large predator becomes a series of shifting segments, difficult to track, harder to judge for speed or distance. This is not camouflage in the sense of hiding completely. It is camouflage through confusion, a ghosting effect that works precisely because the ocean itself refuses to stay still. The tiger shark does not rush this advantage. It patrols. Its movement is steady, deliberate, and unhurried, a wide arc through coastal zones, reef edges, and open sand flats. Unlike predators that specialize in a narrow set of prey or tactics, the tiger shark's strength lies in flexibility. It investigates everything: floating debris, injured fish, unfamiliar silhouettes. This curiosity is not reckless. It is a hunting strategy tuned to environments where opportunity appears briefly and unpredictably. As an opportunistic patroller, the tiger shark covers ground rather than guarding territory. Its routes often intersect with ecological crossroads, places where prey species transition between habitats. Reef fish moving out to feed over sand, turtles surfacing for air, birds diving and leaving behind injured fish. These intersections are rich with information, and the tiger shark reads them as it moves, adjusting depth, speed, and orientation in response to subtle cues. Vision plays a role, but it is not dominant. In clear daylight, prey may detect the shark early and scatter. But the tiger shark does not depend on surprise alone. It relies on persistence and sensory balance. Its lateral line detects vibrations from struggling or panicked animals. Its sense of smell gathers chemical traces that linger long after visual contact is lost. These inputs allow the shark to maintain awareness even when prey slips out of sight, turning temporary encounters into extended opportunities. As light fades, the balance shifts decisively. Night and low light conditions favor the tiger shark in ways that reshape the rules of the encounter. Many prey species depend heavily on vision to detect threats, and as contrast drops, their reaction times lengthen. The tiger shark, however, retains control. Its eyes, adapted for dim conditions, continue to resolve motion where others see only blur. More importantly, its reliance on non-visual senses becomes an advantage rather than a fallback. In darkness, a fish's erratic movement produces vibrations that carry farther and clearer than its silhouette ever could. Chemical signals disperse slowly, creating trails that linger in the water column. The tiger shark follows these invisible paths with ease, closing distance while remaining largely undetected. In these conditions, the striped body becomes almost irrelevant visually, yet still contributes to the overall effect by blending into the faint patterns of moonlit water and reef shadow. This is where the myth of the tiger shark as a mindless eater often emerges, fueled by its famously broad diet. Stories of strange objects found in stomachs have painted it as a roaming garbage disposal, indiscriminate and uncontrolled. The reality is more nuanced and more revealing. The tiger shark's diet is broad because its environment demands adaptability. Coastal zones are unpredictable. Prey availability shifts with tides, seasons, and human activity. A predator that refuses unconventional food risks starvation. The tiger shark's stomach reflects this ecological reality. Thick walls and strong acids allow it to process a wide range of materials, from hard-shelled prey to dense bone. This toughness does not define the shark's intent. It defines its resilience. When it consumes unusual objects, it is not because it prefers them, but because its curiosity and investigative behavior occasionally lead to mistakes. The shark tests unfamiliar items much as it tests prey, gathering information through contact. Most of what it consumes is still living, moving, energy-rich food. Fish, turtles, birds, marine mammals. The predator comes first. The tolerance for error comes second. This investigative behavior extends into interactions with unfamiliar silhouettes near the surface, including humans. The tiger shark's tendency to patrol close to shore places it in frequent proximity to swimmers, surfers, and divers. Shallow water amplifies sensory signals. Splashing, paddling, and uneven movement create vibration patterns, unlike those of natural prey, yet close enough to warrant inspection. In murky or low-light conditions, these cues become ambiguous, triggering approach rather than immediate attack. Here again, the concept of the test bite emerges, not as aggression, but as assessment. The shark gathers information quickly and at close range, determining whether the target fits its feeding profile. In most cases, it does not. The shark disengages, often after a single interaction. These encounters, while terrifying, reflect caution rather than predation. The tiger shark is not hunting humans. It is navigating an environment increasingly crowded with unfamiliar stimuli. The fear associated with these close-to-shore encounters is not misplaced, but it is often misunderstood. The tiger shark's presence in shallow water highlights a broader ecological truth. Coastal zones are shared spaces, shaped by both marine life and human activity. As predators adapt to altered environments, overlap increases. The tiger shark's flexibility allows it to persist where more specialized predators might retreat, making it both resilient and visible. Physically, the tiger shark's body reinforces this adaptability. Broad head, powerful jaws, robust build capable of sustained cruising rather than brief bursts alone. It is not designed solely for explosive attacks like the great white, nor for constant motion like pelagic hunters. Instead, it balances endurance with strength, allowing it to patrol large areas without exhausting itself. This balance supports its role as a generalist predator, capable of exploiting whatever the environment offers. The striping that defines its appearance fades with age, becoming less distinct as the shark grows larger. In juveniles, the pattern is bold and high contrast, offering greater camouflage in shallow, complex environments where young sharks are more vulnerable. As the shark matures and faces fewer predators, the need for visual concealment lessens, replaced by sheer size and confidence. This gradual change reflects a life history shaped by shifting risks and priorities, where survival strategies evolve alongside the body itself. Ecologically, tiger sharks exert pressure across multiple trophic levels. By preying on turtles, they influence grazing patterns on seagrass beds. By consuming sick or injured animals, they contribute to population health. Their opportunism ensures that few resources go unused, tightening nutrient cycles in coastal systems. Fear of tiger sharks also alters prey behavior, reducing time spent in exposed areas and reshaping movement patterns across reefs and beaches. Watching a tiger shark emerge from blue haze is a study in controlled presence. The striped head resolves slowly, not rushing into clarity, but materializing as the water itself shifts. There is no dramatic acceleration, no sudden violence. just a steady approach, curiosity guiding movement, senses tuned to every signal in the water. It is this calm persistence that makes the tiger shark unsettling. It does not need speed or surprise alone. It has time. In the end, the tiger shark embodies a different kind of dominance. Not the precision strike of the great white, not the endless motion of pelagic hunters, but adaptability. A predator built to investigate, to endure, and to thrive in uncertainty. In a blue world defined by change, its striped body moves like a ghost through shifting light, a reminder that sometimes the most dangerous hunters are not those that charge, but those that simply keep coming. The water here feels deceptively calm, a clear blue corridor where light travels freely and distance seems easy to judge. There is no murk, no shadowed reef wall, no dramatic drop into darkness. Everything looks exposed, readable, safe. Small fish drift in loose formations, their scales flashing as they turn, sunlight bouncing off their bodies in brief sparks. In this openness, danger does not announce itself with size or movement. It arrives disguised as nothing at all. A long, narrow shape hangs motionless in the water column, so still it appears detached from the scene, like debris caught in suspension. Its body reflects the blue around it, mirroring the gradient of light so precisely that its outline dissolves into the background. From a distance, it could be mistaken for a floating strip of metal, a piece of drift material, or simply a trick of light. This is the Barracuda at rest, and stillness is its first weapon. Unlike predators that rely on constant motion or active stalking, the Barracuda understands the power of restraint. Its metallic skin acts like a living mirror, reflecting surrounding colors and light patterns rather than absorbing them. In bright water, this reflection breaks up contrast, erasing the visual cues that prey rely on to identify threats. A moving predator draws attention. A stationary reflective shape does not. The Barracuda uses this principle to vanish in plain sight, waiting not for the perfect moment, but for the inevitable mistake. That mistake usually comes from the prey itself. Schooling fish gather for safety, believing that numbers dilute risk. And in many cases, they are right. A coordinated school can confuse predators, presenting a swirling mass of bodies that makes it difficult to isolate a single target. But this strategy depends on cohesion and timing. When schools tighten too much or shift too suddenly, they create turbulence, flashes of movement, and erratic trajectories. To a predator built for rapid assessment, this chaos is not protection, it is opportunity. The Barracuda's eyes are positioned forward, granting it depth perception and precise targeting ability. As it remains still, it watches the school intently, tracking individual movements within the larger mass. It is not scanning randomly. It is searching for inconsistency. A fish that turns a fraction too late. One that strays from alignment. One whose movements lag behind the group's rhythm. These small deviations stand out sharply against the otherwise synchronized motion, drawing the Barracuda's focus like a beacon. When the strike comes, it is almost impossible to see in real time. The Barracuda does not accelerate gradually. It explodes. Muscles along its streamlined body contract in a sudden burst, propelling it forward with astonishing speed over a very short distance. This is not a chase designed to wear prey down. It is a surgical lunge, calculated to end the encounter before the prey fully understands it has begun. This short-range acceleration is where the Barracuda's design becomes unmistakable. Its body is long and narrow, reducing drag and allowing energy to translate directly into forward motion. The tail delivers a powerful snap rather than a sustained beat, maximizing initial thrust. The jaws open at the last possible moment, minimizing water resistance until contact is imminent. In these fractions of a second, the Barracuda transforms from inert reflection into lethal force. The teeth complete the equation. Barracuda teeth are long, sharp, and angled slightly backward, designed not for crushing, but for slicing and holding. Slippery fish bodies offer little resistance to blunt force, but they yield easily to shearing edges. As the Barracuda strikes, its teeth cut cleanly through scales and muscle, often incapacitating prey instantly. Once contact is made, escape becomes unlikely. The backward angle of the teeth prevents prey from slipping free, even if the initial strike does not kill outright. This method is particularly effective against schooling fish precisely because of the confusion schools create. In the chaos of a sudden attack, individual fish often scatter in different directions, colliding or crossing paths. This momentary disorder increases the chance of misjudged movements, and the barracuda capitalizes on it. It does not need to pursue the fastest fish. It needs only to exploit the breakdown of coordination. After the strike, the barracuda often returns quickly to stillness, resuming its suspended posture as if nothing has happened. This behavior conserves energy and maintains the illusion of safety for nearby prey. Schools that regroup too quickly around the same area risk repeating the cycle, unaware that the reflective shape in their midst is actively assessing them once again. The effectiveness of this strategy explains why barracudas are often observed hovering near reefs, drop-offs, and open channels where fish traffic is constant. These locations act as natural funnels, concentrating prey movement and increasing encounter rates. The barracuda does not patrol endlessly. It positions itself where prey must pass, letting the environment do part of the work. There is a subtle irony in the barracuda's reliance on reflection and stillness. Its appearance is often described as aggressive, even intimidating, with a prominent jawline and exposed teeth. Yet these features matter less than its ability to disappear. The teeth are useless if prey never comes close enough. The strike is meaningless if the target is alert. Success depends on patience and precision rather than intimidation. Human encounters with barracudas are rare but memorable, often fueled by misunderstanding rather than intent. Shiny objects such as jewelry, watches, or metallic equipment can attract a barracuda's curiosity, mimicking the reflective flashes of fish scales. In these cases, the animal is not attacking out of aggression, but investigating a potential prey signal. Once identified as unsuitable, the barracuda typically loses interest and moves on. This behavior underscores the same principle seen in its natural hunting. It responds to visual cues first, evaluates quickly, and disengages if the information does not match expectations. Ecologically, barracudas occupy a critical role as mid to upper-level predators in coastal systems. By targeting weak or poorly coordinated individuals, they help maintain school health and prevent overcrowding. Their presence influences schooling behavior, encouraging tighter coordination and quicker response times. In this way, the barracuda acts not just as a consumer of fish, but as a regulator of behavior within prey populations. The barracuda's metabolism reflects its hunting style. High-speed bursts demand significant energy, but the reliance on stillness between strikes allows recovery without constant feeding. This balance enables barracudas to remain effective hunters, even in environments where prey density fluctuates. They are not bound to continuous motion or constant pursuit. They wait, observe, and strike only when conditions align. Seen in profile against a blue water gradient, the barracuda looks almost unreal, a living blade suspended in space. Its metallic body catches light along its flank, fading smoothly into darker tones toward the back and belly. When the jaws open, rows of teeth gleam briefly before vanishing again into reflection. It is a reminder that in the ocean, danger does not always roar or charge. Sometimes it waits, perfectly still, until motion itself becomes the invitation. The barracuda's success lies in its understanding of perception. It knows that prey sees patterns, movement, and flashes, not intent. By becoming part of the background until the exact moment of action, it turns the clarity of open water into a false sense of security. In doing so, it proves that even in the brightest, most exposed environments, invisibility is not about hiding, but about being mistaken for nothing at all. The water here does not offer clarity. It moves thick and slow, heavy with sediment, stained by soil and decaying leaves, carrying the color of the land itself. Light struggles to penetrate more than a short distance before dissolving into brown and green haze. Vision is unreliable in this world. Shapes blur. Distances collapse. What matters instead are signals that travel without sight. Pressure waves, chemical traces, Sudden disturbances that ripple outward through the water like warnings written in a language older than eyes. This is where the piranha lives, not as a constant frenzy of teeth, but as a creature waiting for conditions to shift. The legend of the piranha swarm did not come from nowhere. There are moments when the water seems to erupt, when flashing bodies converge in violent bursts, when flesh disappears with shocking speed. But these moments are not the norm. They are the exception, triggered by a precise alignment of stressors that flip the behavior of an otherwise cautious fish. To understand piranhas, the spectacle must be stripped away and rebuilt from the environment upward. For most of their lives, piranhas are restrained predators. They move in loose groups, yes, but not in constant attack mode. They feed opportunistically, taking injured fish, scavenging carrion, and testing prey with quick, calculated bites. The river is vast, resources fluctuate, and energy must be conserved. In stable conditions, reckless aggression would be wasteful and dangerous. The famous chaos only emerges when stability breaks. That break often comes with water level changes. During dry seasons, rivers shrink. Floodplains retreat. Fish densities increase as habitats compress into smaller channels and pools. Oxygen levels drop. Stress hormones rise across the ecosystem. In these moments, competition intensifies and hesitation becomes costly. A wounded animal bleeding into confined water sends a chemical signal that travels fast and far, amplified by scarcity. This is when the piranha's reputation comes alive. Smell is the first trigger. Piranhas possess highly sensitive olfactory systems capable of detecting minute traces of blood and organic compounds in murky water where vision fails completely. Once detected, these chemical cues do not incite blind attack. They initiate orientation. Fish turn toward the source, closing distance cautiously at first. As more individuals detect the same signal, numbers grow. Pressure waves generated by movement add another layer of information, confirming activity, struggle, vulnerability. Vibration. Sensing becomes critical here. Through their lateral line system, piranhas detect sudden, erratic motion that signals injury or panic. A struggling fish does not move like a healthy one. Its movements are uneven, uncoordinated, broadcasting weakness through the water itself. This sensory confirmation pushes behavior from curiosity to commitment. Group dynamics transform the risk equation. Alone, a piranha is cautious. It knows its own vulnerability. Teeth are effective, but bodies are not armored. In numbers, that calculation changes. The first bite is the most dangerous, exposing the attacker to counterstrike. But once that initial contact is made, the prey's movements become more erratic. Blood concentration increases, and the feedback loop accelerates. Each additional piranha reduces individual risk. What looks like madness is actually probability shifting in real time. This is where the swarm illusion forms. From above, it appears as instantaneous violence. From within the water, it is sequential escalation. One bite draws attention, another follows. The prey's attempts to flee generate more vibration, more chemical cues, more attraction. The group feeds not because of frenzy, but because conditions now favor speed over caution. The teeth are often misunderstood in this context. Piranha teeth are sharp, triangular, and interlocking, designed not for crushing power, but for precision slicing. Bite force myths exaggerate their strength, distracting from their true function. These teeth act like shears, capable of removing chunks of flesh cleanly and efficiently. A single bite can disable fins, sever muscle, or expose vital tissue. It is not the power of the bite that overwhelms prey, but the cumulative effect of many fast, accurate cuts delivered in quick succession. This design suits both predation and scavenging. Piranhas do not need to overpower large prey outright. They can dismantle it piece by piece, especially when it is already weakened. This flexibility allows them to switch between feeding modes seamlessly. A carcass drifting into view is not ignored, nor is a wounded fish limping through shallow water. The same tools apply to both situations. Ecologically, this dual role is critical. Piranhas are not just killers, they are recyclers. By consuming dead and dying animals, they prevent the buildup of decaying matter that could otherwise spread disease. By targeting injured prey, they remove weak individuals, indirectly supporting population health. Their presence shapes behavior across the ecosystem. Fish schools avoid certain areas during low water. Animals crossing rivers choose timing carefully. The fear of piranhas influences movement long before teeth are involved. The irony is that outside of crisis conditions, piranhas are often nervous, easily startled fish. Sudden shadows send them scattering. Large disturbances push them deeper into cover. They rely on the environment to tip the balance in their favor. When water is high and resources are abundant, aggression drops. When water recedes and pressure mounts, restraint gives way to efficiency. This conditional behavior is what makes piranhas so effective and so misunderstood. They are not locked into a single mode of existence. They are responsive, adapting to seasonal rhythms, water chemistry, and population density. Their infamous moments are not acts of mindless violence, but adaptive responses to environmental stress. Visually, those moments are unforgettable. Bodies flash silver and red through chaotic water. Sunlight fractures on scales as fish twist and collide. Movement becomes noise. Water churns with sudden force. But even here there is structure beneath the chaos. Each piranha targets exposed tissue. Each bite follows opportunity. The swarm does not consume randomly. It dismantles systematically. To watch a piranha feeding event is to witness an ecosystem under pressure, revealing its emergency protocols. Everything speeds up. Decisions compress. Risk tolerance collapses. What appears as horror is actually survival operating at maximum efficiency. Understanding piranhas requires stepping back from the spectacle and looking at the conditions that produce it. Low water, scarcity, stress, injury. These are the switches that flip caution into coordination. Without them, the river returns to its quieter rhythms, and the piranha returns to its role as watchful opportunist rather than relentless executioner. In the end, piranhas are not monsters lurking in wait for any passing animal. They are indicators. When they become dangerous, it is often because the system itself is strained. Their violence is not random. It is environmental feedback made visible, flashing through murky water in sharp, efficient cuts. Down near the bottom, the world changes character. Light thins, then fractures, then gives up entirely. What remains is not darkness so much as ambiguity, a space filled with suspended particles, drifting debris, fallen leaves, rotting wood, and slow currents that carry scent and vibration far more reliably than sight. This is not a place built for eyes. It is built for contact, for touch, for signals that slide along skin and water rather than travel in straight lines. And in this bottom world, the catfish does not lurk so much as belong. From above, the riverbed or coastal floor can look empty, a flat expanse of sand interrupted by logs, rocks, or mats of vegetation. But to a catfish, this terrain is layered and alive, mapped not by shape, but by texture and chemistry. The whiskers that frame its mouth, known as barbels, are not ornamental. They are sensory instruments, packed with taste and touch receptors that sample the environment continuously. Every movement of water carries information across them. Every grain of disturbed sediment tells a story. The catfish does not search visually for prey. It feels the presence of life before that life ever knows it is being watched. This sensory advantage defines the catfish's stealth. In low light or complete darkness, where other predators hesitate or retreat, catfish remain fully operational. Their barbels sweep forward and outward, tracing invisible lines through the water, detecting chemical cues released by insects, fish, or decaying matter. A struggling animal announces itself not with sight, but with disturbance. Tiny pressure waves ripple through mud and water, and the catfish reads them instantly. In this environment, blindness is not a weakness. It is irrelevant. Movement is deliberate. The catfish does not glide openly across the bottom. It advances slowly, body close to the substrate, using shadows cast by logs and debris to mask even its silhouette. Its skin lacks reflective scales, absorbing light rather than flashing it back. This matte surface blends seamlessly into mud and sand, making the fish difficult to distinguish even at close range. When it pauses, it becomes part of the terrain, another contour in a landscape already cluttered with shapes. The strike, when it comes, is abrupt and surprisingly powerful. Many catfish species rely on suction feeding, a method that turns the act of eating into a hydraulic event. By rapidly expanding the mouth cavity, the catfish creates a sudden drop in pressure, pulling water and prey inward with force. To an insect skimming the bottom, or a small fish hovering too close, the effect is instantaneous. There is no chase, no visible pursuit. One moment the prey exists in open water. The next, it is gone, swallowed whole in a single gulp. This feeding strategy works across a wide range of prey types. Some catfish specialize in insects and invertebrates, vacuuming them from crevices or sifting them from sediment. Others target fish, ambushing them from below or from the side, relying on the same suction to overcome the prey's reaction time. Still others supplement active hunting with scavenging, consuming dead or dying animals encountered along their routes. This diversity is not indecision. It is adaptability expressed through anatomy. The unpredictability of catfish diets makes them difficult for prey to anticipate. A small fish may avoid visual predators in open water, only to drift into danger near the bottom. An insect that survives aerial hunters may fall victim to a sudden upward gulp. Even carcasses that seem safe from predation become feeding opportunities. In ecosystems where energy must be captured whenever it appears, catfish waste little. Defense is equally pragmatic. Catfish are not fast sprinters, nor are they built for prolonged combat. Instead, many species are equipped with stiff, sharp spines along their dorsal and pectoral fins. These spines can lock into place, transforming the catfish into an awkward, painful mouthful. Predators that attempt to swallow a catfish risk injury to their mouths or throats, sometimes fatal. This deterrent allows catfish to occupy tight spaces with confidence, wedging themselves beneath logs or between rocks where escape routes are limited. This ability to sit boldly in confined terrain further enhances their ambush potential. A catfish tucked beneath debris does not need to flee at the first sign of danger. It holds position, trusting its defenses. Prey passing overhead may never register the threat until the substrate itself seems to open and pull them downward. The bottom world becomes not just a hiding place, but an active hunting platform. Thermoregulation also plays a role in this strategy. Water near the bottom often maintains more stable temperatures than surface layers, especially in shallow systems. Catfish take advantage of this consistency, remaining active during periods when other species slow down due to thermal stress. In warmer conditions, they retreat to deeper, cooler pockets. In cooler periods, they continue feeding while others reduce activity. This flexibility extends their effective hunting window across seasons and conditions. The ecological impact of catfish is subtle but significant. By feeding on insects, they influence populations of aquatic larvae that might otherwise emerge in overwhelming numbers. By scavenging, they help recycle nutrients, breaking down organic matter and redistributing energy through the food web. By preying on fish, they shape community structure, often targeting weak or poorly adapted individuals. Their presence stabilizes systems not through dominance, but through persistence. Watching a catfish approach prey is an exercise in patience. There is no dramatic acceleration, no obvious tension. The fish advances centimeter by centimeter, barbells testing the water ahead, body aligned with current and contour. The prey may sense something amiss, but without a visual cue, reaction is delayed. In murky water, hesitation is enough. When the gulp happens, it feels disproportionate to the calm that preceded it. Sediment erupts briefly, then settles. The catfish resumes its slow movement, already scanning for the next signal. There is no display of success. Feeding is simply another function executed efficiently and without flourish. This understated lethality is what defines catfish as predators. They do not advertise their presence. They do not rely on speed or spectacle. They exploit the fundamental limitations of sensory perception in environments where sight fails. By shifting the rules of detection from vision to touch and chemistry, they gain control over spaces others avoid or misunderstand. The bottom world is often dismissed as inert or empty, but through the perspective of the catfish, it is dense with opportunity. Every object alters flow. Every movement sends ripples. Every scent leaves a trail. The catfish reads these signals constantly, navigating a landscape invisible to most observers. In close view, the whiskers become the focus, gently undulating as they sample the water. The mouth remains closed, unremarkable, until it suddenly becomes a vacuum. The eyes, small and understated, do not search for shapes. They are secondary. In this world, seeing is optional. The catfish survives not by dominating the water column, but by mastering the shadows beneath it. In mud, debris, and darkness, it has built a strategy that turns sensory limitation into advantage. It reminds us that in many ecosystems, the most effective predators are not those we see clearly, but those we barely notice at all. The reef is not an open battlefield. It is a maze. Corridors twist between coral heads, shadows thicken beneath overhangs, and every opening feels like a doorway into something unknown. Water moves differently here, slowed and redirected by stone and skeleton, carrying sound and scent in unpredictable ways. For prey, this complexity promises refuge. For the grouper, it offers control. At first glance, the grouper seems ill-suited to stealth. Its body is thick, heavy, built more like a brawler than a stalker. It does not slice through water with elegance, nor does it vanish into open blue. Instead, it rests, wedged beneath ledges, hovering just inside caves, positioned so that its bulk fills the space behind it. The grouper does not chase prey across the reef. It waits at the places prey must pass through. This is the grouper's defining advantage. It understands architecture. Coral reefs are not random growths but layered structures shaped by time, currents, and collapse. Narrow gaps funnel movement. Overhangs create blind corners. Small fish navigating the reef rely on these structures for protection, darting into crevices when danger approaches. The grouper turns this instinct against them. By claiming the entrances to these spaces, it converts escape routes into traps. Territory for a grouper is not a vague area of influence. It is specific and defended. A cave mouth, a crack between coral blocks, a shaded doorway where light drops abruptly and visibility fails. These locations are valuable, and groupers return to them repeatedly, learning the traffic patterns of the reef as intimately as a city dweller learns intersections. They do not roam widely because they do not need to. Control of entrances brings prey to them. From its position, the grouper appears calm, almost inert. Its coloration blends with the reef's mottled textures, spots and bars breaking up the outline of its body. The illusion of stillness is important. Prey fish passing nearby register the grouper as part of the background rather than an immediate threat. They are more alert to movement than to mass, more sensitive to approach than to presence. The grouper exploits this bias, remaining motionless until the final moment. That moment is defined by the mouth. Groupers possess one of the most dramatic feeding mechanisms on the reef, a system built not for biting, but for inhaling. When the strike begins, the grouper does not lunge far. It opens its mouth, and the mouth expands outward and forward in a sudden, violent motion. Bones rotate. The jaw drops. The throat flares. In an instant, the volume of the mouth cavity increases so rapidly that water rushes inward, carrying prey with it. The effect is less like a bite and more like a localized vacuum collapse. To prey, the experience is incomprehensible. There is no warning, no time to react. One moment, the fish is navigating a familiar corridor. The next, the corridor itself seems to pull inward, swallowing it whole. Suction feeding eliminates the need for precise aim or prolonged struggle. As long as the prey is close enough to the mouth, escape becomes physically impossible. Water moves faster than muscle can react. This feeding strategy pairs perfectly with the grouper's territorial control. By cornering prey against reef walls or drawing them into confined spaces, the grouper reduces the escape directions available. When the suction event occurs, prey has nowhere to go. Even fast, agile fish lose their advantage when space collapses around them. The reef amplifies this effect acoustically. Sudden pressure changes create low-frequency sounds that resonate through coral structures. Some groupers produce deep booming noises, felt as much as heard, that may serve multiple purposes. These sounds can assert territorial ownership, warning other groupers to keep their distance. They may also startle prey, freezing them momentarily or causing erratic movement that drives them toward the grouper's position. In the dense reef environment, sound travels farther and bends around obstacles, becoming another invisible tool in the grouper's arsenal. These booms are not constant. They are used selectively, often during heightened activity or territorial disputes. Their low pitch makes them ideal for underwater transmission, cutting through ambient noise where higher frequencies dissipate. For the reef, this creates an auditory landscape where presence is communicated even without visual contact. The grouper announces itself not by chasing intruders away, but by making its control known. Occasionally, this control extends beyond solitary hunting. Observations have documented groupers engaging in brief cooperative interactions with other predators, most famously moray eels. These events are rare and situational, not habitual partnerships, but they reveal the grouper's capacity for behavioral flexibility. By signaling to a moray, often through specific body movements or postures, a grouper can flush prey from crevices too narrow for its own bulk. The moray drives prey out. The grouper waits at the exit. No coordination beyond this moment is required. Once the opportunity passes, the alliance dissolves. What makes this behavior remarkable is not its frequency, but its implication. It suggests an awareness of another predator's capabilities and an ability to exploit complementary skills without competition. On a reef where resources are contested intensely, this temporary alignment reflects strategic thinking rather than instinct alone. Despite its power, the grouper is not reckless. It conserves energy by minimizing unnecessary movement. Its thick body and large mass make long pursuits inefficient, so it avoids them entirely. Instead, it invests in patience and positioning. A successful strike delivers a large meal relative to effort, offsetting the long periods of stillness that precede it. This strategy shapes the reef community. Small fish learn to avoid certain caves and ledges, altering their routes and feeding times. Some species restrict their movements to open water when groupers are active, despite increased exposure to other predators. Others adopt tighter schooling behavior near the reef to reduce individual risk. In this way, the grouper influences not only who survives, but how entire populations move and behave. The grouper's role extends into reef health as well. By controlling populations of smaller predatory fish, it indirectly protects herbivores that graze algae. This balance helps prevent algal overgrowth that can smother coral. The grouper's presence stabilizes the system not through dominance alone, but through selective pressure applied at critical points in the food web. Watching a grouper feed is a study in contrast. Its size suggests blunt force, yet its success depends on finesse. Its appearance implies aggression, yet its behavior is measured. The violence of the suction strike lasts less than a second, after which the fish resumes its position, mouth closing, gills pulsing slowly, as if nothing has happened. The reef returns to motion. Smaller fish reappear cautiously. The doorway remains occupied. Visually, the moment is unforgettable. The grouper lunges forward just enough to bring its mouth into frame, jaws flaring wide, the reef doorway looming behind it like a stage set. The prey vanishes. Sediment puffs outward. Light shifts. Then stillness again. In the complex geometry of the reef, speed alone is not enough. Success belongs to those who understand structure, who turn shelter into constraint and escape into capture. The grouper does not need to dominate open water. It dominates thresholds. It owns the spaces between spaces, the narrow points where choices disappear. In doing so, the grouper reveals a different model of predation. Not pursuit, but possession. Not roaming, but control. On a reef defined by passageways and shadows, the most dangerous hunter is not the one that moves the most, but the one that decides where movement ends. The reef slope opens wide here, a broad descending wall where coral towers thin out and the blue deepens with every meter of depth. This is not the crowded maze of shallow reef flats, nor the tight corridors ruled by ambush specialists. This is open territory, exposed and expansive, where movement is visible from far away, and only animals with confidence can afford to patrol openly. Out of the blue haze, a massive shape glides into view, unhurried and unmistakable. Thick lips, a bulging forehead, a body so large and solid it seems almost out of place among the delicate architecture of coral. At first glance it looks almost comical, a cartoon face drifting through a serious ecosystem. That impression lasts only until it feeds. The Napoleon fish, also known as the humphead wrasse, carries one of the most misleading appearances on the reef. Its exaggerated lips and rounded head give it a soft, almost clumsy expression, an animal that looks more curious than dangerous. But this is a deception born of perspective, not reality. Beneath that goofy exterior is one of the most mechanically powerful mouths on the reef, a living, crushing machine capable of dismantling prey that many predators cannot even attempt. As it patrols the slope, the Napoleon fish moves with deliberate authority. It does not dart. It does not hug cover. It swims openly, fins sweeping slowly, body rolling slightly as it adjusts course. Smaller fish do not scatter in panic at its approach, but they do make space, drifting aside instinctively. This is not fear born of sudden threat. It is recognition. The Napoleon fish is not a chaser, but it is dominant, and the reef treats it accordingly. Its feeding strategy reflects this dominance. Unlike predators that specialize narrowly, the Napoleon fish operates as a reef tank, capable of processing a wide range of prey types through sheer mechanical power. Hard-shelled animals that frustrate other fish are routine targets here. Sea urchins bristling with spines, thick-shelled mollusks anchored to rock, crustaceans armored against slicing teeth. The Napoleon fish approaches these prey without hesitation, positioning its massive jaws precisely before biting down with crushing force. The jaws are reinforced by dense bone and powerful muscles anchored to the skull, allowing the fish to generate immense pressure. When it bites, shells fracture, spines snap, protective armor fails catastrophically. The sound can be heard underwater, a dull crack that echoes faintly across the reef. For prey adapted to resist most predators, this is a fatal mismatch. Evolution built them for evasion or abrasion, not for direct compression by an animal this large and strong. Yet crushing is only part of the story. The Napoleon fish is equally capable of suction feeding, expanding its mouth cavity to pull in softer prey with surprising speed. Fish sheltering too close to the reef face, startled by the sudden approach of this massive body, can vanish in a single inhale. The same mouth that pulverizes stone-hard defenses can shift instantly into a vacuum, demonstrating a versatility that few reef predators can match. This dual feeding mode makes the Napoleon fish ecologically unique. It does not compete directly with specialized hunters or grazers. Instead, it occupies a high-level role, accessing food sources that sit beyond the reach of others, while still exploiting more conventional prey when the opportunity arises. In doing so, it influences reef balance in subtle but significant ways. By preying on sea urchins, it helps prevent overgrazing that can strip reefs of algae controlling coral health. By consuming a range of organisms, it redistributes energy across the system, linking hard substrate communities with open water dynamics. Intelligence amplifies this role. The Napoleon fish is not skittish. It does not flee at unfamiliar sights or sudden movements. Divers often report individuals approaching closely, inspecting bubbles, cameras, and bodies with calm curiosity. This boldness is not recklessness. It reflects confidence built on size, strength, and experience. Few predators pose a serious threat to a full-grown Napoleon fish, and it behaves accordingly. This confidence extends into its interactions with other reef inhabitants. The Napoleon fish does not need to assert itself aggressively. Its presence alone reshapes behavior. Smaller predators give way. Grazers alter feeding routes. The reef seems to reorganize subtly as it passes, as if acknowledging a shift in hierarchy. This is dominance expressed through stability rather than aggression. Its patrol patterns reinforce this impression. The Napoleon fish does not wander aimlessly. It follows large reef slopes, drop-offs and outer reef faces, areas where prey diversity is highest and movement corridors converge. These patrols are slow and methodical, repeated over time, allowing the fish to develop a detailed familiarity with its territory. It learns where urchins cluster, where mollusks anchor, where fish schools tend to linger near structure. This knowledge reduces the need for frantic searching. Food is encountered predictably, reinforcing the animal's calm demeanor. There is an irony here that becomes clear only with close observation. The Napoleon fish looks slow because it can afford to be. Its energy budget does not rely on frequent high-speed pursuits or constant feeding. A single successful crushing event delivers a dense meal. This efficiency allows long intervals between feeding, freeing the fish to patrol, observe, and maintain territory, rather than constantly hunt. The large forehead hump that gives the fish its distinctive profile plays a role beyond appearance. It houses part of the cranial structure supporting jaw musculature, contributing to bite strength. What appears as an awkward bulge is actually an architectural feature tied directly to feeding performance. Form follows function, even when the result looks odd to human eyes. Sound adds another dimension to the Napoleon fish's presence. While not known for dramatic vocalizations like some reef fish, the physical act of crushing prey produces audible cues that travel through the reef. These sounds signal activity, indirectly communicating dominance and feeding success to other animals in the area. On a reef where sound often travels farther than sight, this auditory footprint matters. Despite its power and confidence, the Napoleon fish carries an air of rarity. Encounters are memorable precisely because they are not constant. Large individuals are uncommon, and their absence from many reefs has become noticeable. This scarcity adds to their mystique, transforming each sighting into a moment of significance. The reef feels different when a Napoleon fish appears, heavier, more grounded, as if a missing piece has briefly returned. This rarity is not intrinsic to the species, but the result of pressure. Large size and slow maturation make the Napoleon fish vulnerable to overexploitation. When removed, the effects ripple outward. Urchin populations can increase. Coral health can decline. The absence of a single dominant feeder alters balance in ways that take years to become visible, but are difficult to reverse. Yet this chapter is not about loss. It is about presence. About understanding what the reef looks like when one of its most formidable residents is still there. Watching a Napoleon fish glide along a slope, lips protruding, head massive, body casting a slow-moving shadow across coral, is to witness authority without urgency. The fish does not hurry because the reef accommodates it. It has earned its place. Visually, the experience is striking. The huge lips come into focus first, thick and pale against a blur of color. Then the powerful head, eyes steady and unbothered. The background dissolves into coral and blue as the fish moves past, unchallenged. It does not need to lunge at the camera. Its size alone fills the frame. The Napoleon fish reminds us that danger on the reef does not always wear sharp lines or sleek profiles. Sometimes it looks friendly. Sometimes it looks curious. Sometimes it looks almost ridiculous. But beneath that surface lies one of the reef's most effective machines, built not for speed or stealth, but for dominance through strength, intelligence, and ecological importance. In the vast hierarchy of reef life, the Napoleon fish is proof that power does not always need to look intimidating to be absolute. The water here feels alive in a different way. Instead of hard coral edges and sharp reef shadows, the scene is softened by motion. Long strands of kelp rise from the seafloor and sway back and forth in slow, synchronized arcs. Seagrass meadows ripple like fields in wind, each blade bending and recovering, never quite returning to the same position twice. Light filters through this forest unevenly, broken into shifting patches of green and blue that drift across everything below. In this world, stillness is suspicious. Movement is normal, and anything that does not move like vegetation immediately stands out as wrong. Somewhere among the drifting fronds, something is already watching. At first, it is impossible to isolate. The eye slides past it again and again, catching on leaves, shadows, and overlapping shapes. Then, slowly, the pattern resolves. A leafy silhouette detaches from the background, not because it moves differently, but because it moves exactly the same. This is the leafy sea dragon, an animal that does not hide behind camouflage, but becomes it so completely that even careful observation struggles to separate body from environment. The deception here is total, but it is not static. Unlike animals that rely on coloration alone, the leafy sea dragon understands that camouflage is not just about appearance. It is about behavior. A perfectly colored body that moves incorrectly is immediately exposed. In a habitat defined by constant motion, survival belongs to those who move in rhythm with the environment rather than against it. The leafy sea dragon's body is adorned with elaborate leaf-like appendages that branch outward along its head, torso, and tail. These extensions do not propel it forward. They serve no mechanical function in swimming. Their purpose is visual, breaking up the outline of the animal and extending its shape into the same language spoken by kelp and seagrass. To predators scanning the water, the sea dragon does not read as prey. It reads as background. But shape alone would not be enough. The sea dragon's swimming style completes the illusion. Instead of powerful tail beats or quick directional changes, it relies on small, nearly invisible fins along its neck and back. These fins flutter rapidly, providing gentle propulsion without disturbing the water around it. The body remains largely passive, drifting, rocking, and pivoting exactly as the surrounding vegetation does. When currents push the kelp to one side, the sea dragon goes with it. When the water slackens, it slows. It never fights the flow. It surrenders to it. This behavioral precision is critical. Predators do not need to identify a leafy sea dragon as a specific animal to attack it. They only need to detect inconsistency. A leaf that accelerates suddenly. A strand that turns against the current. The sea dragon avoids these mistakes by letting the environment dictate its motion entirely. In doing so, it disappears not by vanishing, but by conforming. This camouflage serves a dual purpose. It allows the sea dragon to hunt without being seen, and it protects a body that is ill-equipped for confrontation. Unlike many fish, the leafy sea dragon is fragile. Its body lacks armor, speed, or defensive spines. It cannot flee quickly, and it cannot fight effectively. Its survival depends almost entirely on not being noticed. Predation, therefore, must be subtle. The leafy sea dragon feeds on tiny crustaceans, primarily small shrimp-like organisms that drift or cling to vegetation. These prey items are alert and mobile, capable of rapid escape if startled. The sea dragon approaches them not as a predator closing in, but as part of the habitat itself. As it drifts past a blade of seagrass or a kelp frond, its head aligns naturally with the flow, mouth angled forward, eyes scanning independently for movement. When prey comes within range, the strike is nearly invisible. The sea dragon uses suction feeding, snapping its tubular mouth open to draw in water and prey in a single rapid motion. There is no lunge, no chase. The action is over before surrounding particles even register disturbance. To the prey, there is no warning. One moment it is drifting safely among leaves. The next, it is gone. This makes the leafy sea dragon a micro-assassin, operating at a scale and speed that contrasts sharply with its serene appearance. Its entire hunting strategy depends on remaining indistinguishable from the environment until the final instant. Any deviation risks exposure, not only to prey, but to predators that would have little trouble consuming such a defenseless animal. This vulnerability explains much about the sea dragon's behavior. It avoids open water whenever possible, staying within dense vegetation where visual noise is highest. It does not engage in territorial disputes or aggressive displays. It does not chase intruders or compete openly for food. Instead, it relies on patience and persistence, feeding continuously on small prey items that pass within reach. The habitat itself becomes part of the sea dragon's body. Kelp forests and seagrass meadows provide not just cover, but identity. In these environments, visual complexity is extreme. Overlapping leaves, shifting light, and constant motion create a background that is difficult to pass even for experienced predators. The leafy sea dragon amplifies this complexity by adding its own false leaves into the mix, increasing visual clutter rather than standing apart from it. This reliance on habitat makes the sea dragon highly specialized. It thrives only where vegetation is dense and healthy. Remove the kelp or seagrass and the illusion collapses. Without the forest, the dragon is exposed, its elaborate camouflage rendered meaningless in open water. This tight coupling between animal and environment highlights a different kind of evolutionary success, one that trades flexibility for perfection within a narrow niche. The sensory world of the leafy sea dragon reflects this specialization. Vision is important, but not for spotting distant threats. It is used at close range, scanning for tiny movements that indicate prey. The eyes move independently, allowing continuous monitoring without head movement that might betray its presence. Chemical cues play a role as well, guiding the sea dragon toward areas of higher prey density within the vegetation. Energy conservation is another defining feature. The sea dragon's lifestyle is low intensity by necessity. Constant high-speed movement would be incompatible with its camouflage and unsustainable given its diet. Instead, it maintains a slow metabolic pace, feeding steadily rather than in bursts. This rhythm aligns with the productivity of seagrass and kelp ecosystems, where small prey are abundant but individually low in energy. The irony of the leafy sea dragon lies in its reputation. It is often described as magical, mythical, or ornamental, admired for beauty rather than understood for function. But this beauty is not excess. Every frond-like extension, every subtle movement, every color gradient exists for survival. The animal is not displaying itself. It is hiding in plain sight with extraordinary discipline. From a predator's perspective, the leafy sea dragon is a test of perception. Many predators rely on shape recognition to identify prey. Fish look for outlines that suggest fins, eyes, or movement patterns inconsistent with plants. The sea dragon disrupts this recognition process entirely. Its outline is ambiguous. Its movement is compliant. Its behavior does not trigger alarm. For humans observing this animal, the experience is often delayed recognition. It takes time for the brain to register that what looks like drifting vegetation is alive. That delay is the same gap predators experience, and it is the gap the sea dragon depends on. Reproduction adds another layer of vulnerability and specialization, though it unfolds quietly within the same vegetated spaces. Courtship and mating must occur without breaking camouflage, without drawing attention. Eggs are carried and developed in ways that minimize exposure, reinforcing the theme that visibility is the greatest risk this species faces. The leafy sea dragon does not dominate its ecosystem through force. It survives through harmony with motion. It is not fast, strong, or aggressive. It is precise. In a world where many predators rely on speed or power, the sea dragon represents an alternative evolutionary solution, one that replaces confrontation with integration. Visually, the moment of recognition is unforgettable. A leafy silhouette floats in blue-green water, indistinguishable from the surrounding plants until the eye adjusts. Then, slowly, the head becomes apparent. The tubular mouth. The delicate fins flickering just enough to maintain position. The body is revealed not by movement, but by awareness. In kelp forests and seagrass meadows, danger does not always announce itself with teeth or sudden motion. Sometimes it drifts gently, leaf among leaves, perfectly harmless looking, until a tiny prey item strays too close. The leafy sea dragon proves that in some ecosystems, the highest form of stealth is not hiding behind something, but becoming it completely. At first, nothing here suggests danger. The water is shallow, filtered through blades of seagrass and low coral growth, broken into soft bands of green and blue. Light drifts downward in slow pulses as waves pass overhead, never sharp, never harsh. This is a place of patience, a place where movement is measured and stillness is common. Small crustaceans drift with the current. Tiny fish hover near cover. Everything feels gentle, almost fragile. And within this calm, something waits. It does not chase. It does not stalk. It does not patrol. It holds. A seahorse grips a strand of seagrass with its tail, anchoring itself against the sway of the water. Its body remains upright, posture almost comical, head tilted slightly forward, as if observing the world with mild curiosity. The shape is familiar, even charming. Curled tail, long snout, eyes that seem too large for the body. It looks harmless, decorative, easy to dismiss. That dismissal is exactly what makes it effective. The seahorse is a predator, but not in the way most people imagine one. It does not dominate space through speed or size. It dominates attention by disappearing from it. In habitats crowded with vegetation and visual noise, the seahorse survives by becoming part of the background, not through dramatic camouflage alone, but through behavioral invisibility. It does nothing to draw focus. It waits until focus drifts elsewhere. Camouflage is the foundation of this strategy. Seahorses vary widely in color and texture, often matching the hues and surfaces of the plants they inhabit. Some appear smooth and pale, blending with sandy substrates. Others are knobby and textured, mimicking algae-encrusted stems or coral rubble. These features are not static. Many seahorses can adjust coloration over time, refining their disguise as conditions change. But appearance alone would not be enough. Movement is the greater risk. In seagrass meadows and reef fringes, motion is constant. Plants sway. Particles drift. Small animals pulse and pause. Anything that moves differently stands out immediately. The seahorse avoids this trap by surrendering control. Anchored by its tail, it allows the current to move it. Its body rocks gently in sync with the vegetation, never correcting, never resisting. Even its small dorsal fin, which provides propulsion when needed, beats rapidly but subtly, generating minimal disturbance. This alignment with environmental motion renders the seahorse functionally invisible to prey. And prey is always nearby. Tiny crustaceans, copepods, and larval fish drift through these habitats in steady numbers. They are alert but not paranoid, tuned to detect sudden threats rather than stationary shapes. To them, the seahorse is just another stem, another piece of structure. They approach without hesitation, drawn by currents or feeding opportunities, unaware that they are crossing into a kill zone measured in centimeters. The strike, when it happens, is astonishingly fast. The seahorse does not lunge. It does not bite. It inhales. Its long tubular snout functions as a precision vacuum system. When prey comes within range, the seahorse snaps its head upward in a rapid pivot, opening its mouth at the same instant. This sudden expansion creates a sharp drop in pressure, pulling water and prey into the snout before the prey can react. The entire event unfolds in milliseconds. There is no warning, no chase, no visible aggression. One moment the prey drifts freely, the next it is gone. This suction feeding mechanism is highly specialized. Seahorses lack teeth and stomachs, relying instead on constant feeding to meet their energy needs. Their digestive systems pass food quickly, making efficiency essential. Each strike must count. The head snap is powered by elastic energy stored in specialized muscles and tendons, released in a burst faster than muscle contraction alone would allow. It is a biological spring, optimized for speed over force. The irony is striking. An animal so slow in movement, so gentle in appearance, delivers one of the fastest predatory actions in its environment. The contrast between calm stillness and explosive precision defines the seahorse's entire lifestyle. This sit and snipe approach shapes everything about its behavior. Seahorses do not compete aggressively for territory. Instead, they select perches with high prey traffic, anchoring themselves where currents concentrate food. These positions may be revisited repeatedly, forming a predictable hunting circuit. Rather than roaming widely, the seahorse lets the environment deliver prey to it. This strategy minimizes energy expenditure, but it comes with trade-offs. Seahorses are poor swimmers compared to most fish. Their upright posture and small fins limit speed and maneuverability. If forced into open water, they are vulnerable. Camouflage and anchoring are not optional. they are essential. That vulnerability extends beyond predation into reproduction, where the seahorse reveals one of the most unusual biological role reversals in the animal world. In seahorses, it is the male who becomes pregnant. After an elaborate courtship involving synchronized movements and color changes, the female transfers her eggs into a specialized brood pouch on the male's abdomen. Once inside, the eggs are fertilized and carried by the male for the duration of development. He regulates the internal environment of the pouch, controlling salinity, oxygen levels, and nutrient exchange. The pouch functions more like a placenta than a simple container, actively supporting embryonic growth. This role reversal has profound implications. While the male carries the developing young, the female is free to produce more eggs, potentially increasing reproductive output. At the same time, male investment ensures higher survival rates for offspring in environments where free-floating eggs would be quickly consumed. It is an elegant solution shaped by the same pressures that define the seahorse's hunting strategy: vulnerability, concealment, and efficiency. Even during pregnancy, the male seahorse continues to feed and anchor itself, balancing the demands of predation and parental care. Birth, when it occurs, is a physically taxing event, with the male expelling fully formed miniature seahorses into the surrounding habitat. From that moment on, parental care ends. The young must survive on their own, immediately adopting the same camouflage-driven existence as their parents. The habitat itself reinforces this life strategy. Seagrass meadows and reef margins provide both food and cover, but they are also among the most threatened marine environments. Their complexity offers refuge for countless species, and the seahorse is one of the most specialized among them. Remove the grass, and the entire system collapses. Without anchoring points, without visual clutter, the seahorse becomes exposed, its evolutionary advantages stripped away. Ecologically, seahorses occupy a quiet but important role. By feeding on small crustaceans, they influence plankton dynamics and nutrient flow within shallow systems. They are not keystone predators, but they are indicators. Their presence signals habitat complexity and stability. Their absence often marks degradation long before larger species disappear. Watching a seahorse hunt requires patience. There is no spectacle, no dramatic chase. The camera lingers on a single individual, gently rocking with the current. Particles drift past. A tiny shrimp enters the frame, pulsing forward in short bursts. The distance closes slowly. Nothing changes. Then, in a blink, the head snaps. The shrimp vanishes. The seahorse resumes its position, as if nothing has happened. This subtlety is its power. The seahorse survives by being overlooked. It hunts by being ignored. It reproduces by redefining roles. In a world where predation is often loud and fast, the seahorse represents a quieter path, one built on timing, restraint, and precision. Visually, the scene captures this paradox perfectly. The seahorse stands in the foreground, anchored and calm, its curled tail wrapped securely around a stem. Behind it, the habitat sways, alive with motion. Prey drifts closer. The predator does not move until it must. And when it does, it reminds us that danger does not always announce itself with teeth or speed. Sometimes it waits patiently, shaped like something harmless, until the moment is exactly right. The ocean never stops watching them. Even when the surface looks calm, even when the water feels empty and blue, danger is threaded through every layer of space. For seals, survival is not a matter of avoiding predators occasionally. It is a constant condition, woven into how they move, how they hunt, how they rest, and how they look. They live as both predator and prey, and that dual role has shaped them into some of the most alert, agile, and strategically cautious animals in the sea. From a distance, a seal in motion is difficult to fix in place. Its body seems to blur into the water, not because it is fast alone, but because it disappears depending on where you look from. A dark back absorbs the shadowed depths below. A pale belly melts into the glare of surface light above. This countershading is not decorative. It is geometry applied to survival. Whether viewed from above or below, The seal dissolves into its background, leaving predators and prey alike struggling to judge distance, direction, and intent. This visual ambiguity is the foundation of the seal's stealth. Unlike ambush predators that rely on concealment behind structure, seals rely on motion and angle. They turn their bodies to control what is visible, banking and rolling through the water so that contrast collapses at critical moments. A fish looking up sees brightness. A predator looking down sees darkness. In between, the seal becomes a moving gap in perception, something that is present but difficult to resolve. That difficulty buys time. And in the ocean, time is everything. When a seal hunts, the calm exterior gives way to something far more dynamic. Seals are not straight-line chasers. They are underwater dogfighters, capable of sudden turns, loops, rolls, and reversals that defy prediction. Their bodies are flexible, powered by strong hind flippers, and a muscular core that allows rapid changes in orientation. A seal can accelerate, brake, and pivot in tight arcs, matching the evasive maneuvers of fast, agile fish. This agility turns open water into a three-dimensional combat space. Fish attempt to outturn the seal, darting sideways or upward in quick bursts. The seal responds instantly, adjusting angle and speed with precision. Where larger predators rely on brute force or ambush, seals win through maneuverability. They close distance not by overpowering prey, but by staying aligned through every evasive move until escape options collapse. The effect is relentless. Once a seal commits to a chase, it stays close, forcing prey to burn energy at a faster rate. Panic accelerates mistakes. A fish turns too sharply. Another collides with a neighbor. The seal exploits these errors with quick snaps of its jaws, ending the pursuit in seconds or minutes rather than drawn-out exhaustion. But even during the hunt, awareness never fades. A seal is always scanning, always listening. The same senses that track prey are tuned constantly for threats. This is the cost of living in a world where being a predator does not grant safety. Seals are hunted by sharks, orcas, and occasionally large terrestrial predators when hauled out on land or ice. These threats shape behavior as deeply as food does. A seal does not relax in open water. It chooses routes carefully, hugging kelp forests where visibility is reduced and escape paths multiply. It approaches the surface cautiously, often pausing below to listen before breaking into open air. Sound plays a critical role here. Water carries sound efficiently, bending it around obstacles and across distances far beyond visual range. Seals listen for disturbances that do not belong. The low-frequency pressure waves of a large swimming body. The irregular turbulence of an approaching predator. These cues arrive before the predator itself, giving the seal a narrow window to react. Group behavior adds another layer of defense. Near haul-out sites, seals cluster together, not for comfort, but for surveillance. Many eyes and ears scanning simultaneously increase the chance of early detection. When one seal reacts, others follow instantly, slipping into the water or shifting position in response to a threat that only one may have sensed. This collective vigilance reduces individual risk, even if it does not eliminate it. Haul-outs themselves are carefully chosen. Rocky shores, sandbars, and ice edges provide access to both rest and rapid escape. Seals rarely venture far from water when resting, maintaining a direct line back to safety. Even here, they do not sleep deeply. Heads lift frequently. Bodies reposition. The posture of a seal at rest is not abandonment, but readiness held in reserve. The variety of habitats seals occupy reflects this balance between opportunity and risk. Along temperate coasts, kelp forests offer shelter and hunting grounds, dense with fish and visual clutter that disrupts predator attacks. In polar regions, ice edges become lifelines, platforms for rest and breeding that also serve as escape routes from aquatic hunters. In open seas, seals navigate vast distances between feeding grounds and haul-outs, crossing exposed zones with caution and speed. This environmental flexibility is supported by physiological adaptations. Thick layers of blubber provide insulation in cold water, maintaining body temperature while also serving as energy reserves. But blubber is more than warmth. It is fuel that allows seals to dive repeatedly, hunt intensively, and still retain the energy needed for rapid escape when danger appears. The seal's body is built to operate under stress, balancing endurance with explosive response. Even their whiskers play a role in this vigilance. Highly sensitive, they detect minute changes in water movement, allowing seals to track prey in low visibility and sense disturbances behind them. A fleeing fish leaves a wake. A predator displaces water. The seal reads these invisible trails, reconstructing events that occurred seconds earlier. This ability allows it to hunt effectively while remaining aware of threats approaching from outside its field of view. Living under constant threat shapes behavior in subtle ways. Seals rarely move in straight lines when traveling long distances. They vary depth, speed, and direction, making their paths harder to anticipate. They avoid lingering in open water, even when prey is abundant. Every decision is filtered through the question of exposure. This perpetual alertness creates an underlying tension in seal life. They are playful animals by nature, often observed interacting with one another, chasing objects, or riding waves near shore. But even play occurs within limits. Heads turn, movements pause. Awareness never fully shuts off. The ocean does not allow it. From an ecological perspective, seals occupy a critical middle position. They regulate fish populations, targeting fast-growing species that could otherwise overwhelm ecosystems. At the same time, they provide prey for apex predators, transferring energy upward through the food web. This dual role stabilizes marine systems, but it also ensures that seals remain under constant pressure from both directions. Watching a seal move through blue water captures this contradiction perfectly. Its silhouette cuts cleanly through the gradient, torpedo-shaped and smooth. It appears confident, almost effortless, but beneath that grace lies calculation. Every turn is measured, every ascent checked, every pause intentional. When a seal breaks from the depths and rockets toward the surface, it does so at an angle, minimizing the time spent silhouetted against the light. When it dives, it rolls, presenting its dark back to anything above. These small adjustments accumulate into a survival strategy refined over millions of years. The seal is not the fastest predator. It is not the strongest. It does not dominate through intimidation. It survives through awareness, agility, and constant adaptation to a world that hunts it as relentlessly as it hunts others. In the end, seals embody the reality of marine life better than almost any other animal. They are not kings of the ocean, nor helpless victims. They exist in between, thriving through vigilance and skill. Their stealth is not invisibility, but ambiguity. Their power is not force, but responsiveness. A seal slicing through blue water is not just hunting. It is listening, watching, calculating, living as though every moment matters, because in the ocean, for a seal, it always does. From the surface, they look misplaced. Upright bodies bobbing in frigid water, short legs shuffling over ice and stone, wings that do not fly. Against the vastness of the ocean, penguins appear almost comedic, animals built for land that somehow ended up at sea. That illusion lasts only until they dive. The moment a penguin slips beneath the surface, gravity releases its grip, and the animal transforms into something else entirely. What was awkward becomes precise. What was slow becomes explosive. The bird becomes a missile. Underwater, penguins belong. The change is immediate and total. Flippers snap outward, bodies streamline, and the water fills with motion. Penguins do not paddle. They fly. Their wings, stiffened and flattened by evolution, function as hydrofoils, generating lift and thrust with each powerful stroke. Unlike fish, which push water backward with tails, penguins slice through it, converting downward and upward strokes into forward acceleration. The result is astonishing efficiency. A penguin can outmaneuver many fish, matching turns, reversing direction, and accelerating in bursts that defy its clumsy reputation on land. Hydrodynamics governs every detail of this performance. The penguin's body is shaped to minimize drag, smooth and torpedo-like, narrowing toward the tail. Feathers overlap tightly, forming a waterproof surface that traps a thin layer of air against the skin. This air layer reduces friction and adds buoyancy, allowing penguins to glide between strokes, conserving energy. At speed, tiny bubbles stream from the plumage, creating a shimmering trail that further reduces drag. It is not decoration. It is physics exploited for survival. This efficiency matters because penguins hunt in a three-dimensional battlefield where prey is fast, agile, and unpredictable. Fish scatter, turn sharply, and dive to escape. Penguins respond with equally sharp maneuvers, rolling their bodies to bank through turns, flippers beating asymmetrically to pivot within their own length. Their turning radius is tight enough to follow prey through sudden changes without losing momentum. Where many predators overshoot, penguins stay locked in. Speed alone does not secure a meal. Penguins hunt with coordination. In open water, a single penguin chasing a school of fish would face constant evasion, prey scattering in all directions. Instead, many species hunt in groups, forming loose packs that exploit confusion. Penguins approach schools from multiple angles, driving fish inward, compressing space, and limiting escape routes. Each individual adjusts position in response to the movement of others, maintaining pressure without colliding. The school tightens, fish flashing silver as panic spreads. In that chaos, mistakes multiply. This cooperative hunting is not rigid choreography. It is fluid and responsive, shaped by visual cues and rapid decision-making. Penguins read the motion of the school and of each other, reacting in real time. A fish breaks formation. A penguin surges forward. Another cuts off the escape. The pack adapts continuously until capture becomes inevitable. The efficiency of this method allows penguins to exploit prey that would otherwise be too fast or too dispersed. It also reduces individual effort. By sharing the work of herding, each penguin expends less energy per capture, an advantage in cold environments where maintaining body heat is costly. That cost never disappears. Penguins live under constant thermal pressure. Cold water strips heat from bodies rapidly, forcing penguins to balance hunting time against heat loss. Their thick layers of blubber provide insulation and energy reserves, but dives must still be managed carefully. Too long in the water without feeding, and energy balance tips toward loss. Too little time hunting, and reserves dwindle. Every dive is a calculation. This calculation becomes even more complex because penguins are never just hunters. They are also prey. Below the surface, the same water that grants them speed hides danger. Leopard seals, orcas, large sharks in some regions. These predators patrol the same feeding grounds, tuned to the same cues of movement and sound. Penguins know this. Their behavior reflects it constantly. Before diving, penguins often pause at the surface, scanning. Heads turn, bodies angle downward and hold. This hesitation is not indecision, it is listening. Sound travels farther underwater than light, and the presence of a large predator can be detected through subtle pressure waves and disturbances long before it is visible. Only when the water feels clear does the penguin commit. Even then, risk does not end. Penguins dive and surface repeatedly, rarely following predictable paths. They vary angles, depths, and timing to avoid becoming patterns that predators can exploit. When surfacing, they do not drift upward lazily. They rocket. The exit from water is one of the most dramatic movements in the animal world. A penguin accelerates from depth, body aligned, flippers beating hard, building speed until it breaks the surface in a spray of water. It launches clear of the sea, landing on ice or rock in a single motion. This is not play. It is survival. The moment a penguin slows near the surface is the moment it is most vulnerable. Speed minimizes that window. Just as quickly, the penguin may reverse the move, diving again in an instant, disappearing beneath the surface before danger can close in. This rapid transition between air and water defines penguin life. They exist on the boundary, exploiting it for safety. Group behavior extends into this risk management. Penguins often enter and exit the water together, using numbers to dilute danger. At haul-out sites, they cluster at the edge, some diving while others wait, testing conditions. When one returns safely, others follow. This shared decision-making reduces individual exposure, even if it cannot eliminate risk entirely. The fear of predation shapes penguin colonies profoundly. Routes to and from the sea are worn into ice and rock by repeated use, creating predictable highways that allow fast, coordinated movement. Timing of feeding trips aligns with light conditions that favor detection of predators. Even vocalizations change depending on context. Quieter near the water, louder on land. Despite this constant vigilance, penguins must hunt aggressively to sustain themselves and their young. Breeding seasons impose intense pressure. Adults must travel farther, dive deeper, and return with enough food to sustain chicks waiting ashore. This urgency sharpens hunting behavior, increasing dive frequency and coordination. The ocean becomes both provider and threat in equal measure. Physiologically, penguins are built for this balance. Their oxygen storage capacity allows extended dives. Blood and muscle chemistry prioritize oxygen delivery to vital organs, while peripheral systems tolerate temporary deprivation. Heart rates slow during dives, conserving oxygen, then spike during ascent. These adjustments happen automatically, invisible but essential. Vision underwater is another adaptation. Penguin eyes are optimized to function in both air and water, adjusting focus as conditions change. They can detect contrast and movement effectively in dim, blue-green light, allowing them to track fish even at depth. Combined with hydrodynamic agility, this visual acuity makes them formidable underwater hunters. From an ecological perspective, penguins occupy a crucial role. They transfer energy from ocean to land, feeding on marine prey and returning nutrients to colonies through waste and carcasses. Their foraging patterns reflect ocean productivity, making them indicators of ecosystem health. When fish populations shift, penguin behavior changes quickly, signaling broader environmental shifts. Watching penguins hunt reveals a rhythm that is both frantic and disciplined. Dives stack one after another. Bodies streak through water in coordinated bursts. Then a sudden explosion of motion as fish scatter and penguins surge. Moments later, calm returns, and the pack regroups, already preparing for the next descent. This pacing is what makes penguins so compelling to watch. They compress action into tight sequences, rapid transitions between stillness and speed. There is no lingering chase, no prolonged tension. Everything happens in pulses, mirroring the ocean's own rhythms. Visually, the contrast is striking. A penguin rockets from the water, droplets scattering in sunlight. It lands, pauses for a heartbeat, then dives again, slicing back into blue. The same animal that waddles awkwardly on land becomes an underwater projectile without hesitation. Penguins challenge assumptions about what predators look like. They are birds that cannot fly in air, yet dominate beneath the surface. They are social animals that hunt cooperatively, yet remain constantly alert to danger. They are both relentless hunters and perpetual targets. In the end, penguins embody the reality of life at the edge of two worlds. Their success comes not from eliminating risk, but from managing it continuously. They do not rule the ocean. They survive it through speed, coordination, and awareness sharpened by constant threat. When a penguin vanishes beneath the surface, it is not escaping gravity. It is entering its true element, where feathers become armor, wings become engines, and the awkward bird becomes a precision hunter, moving faster than the fear that follows it. The ice edge is not silent. It creaks, flexes, and sighs as slabs press against one another, shifting under the combined forces of wind, current, and temperature. Beneath it, the water glows a deep, filtered blue, light fractured into wavering beams that slide along the underside of the ice like slow-moving searchlights. This boundary between solid and liquid is one of the most contested spaces in the polar seas, and within it moves an animal that does not hunt in the traditional sense, yet dominates through mass, armor, and explosive presence. The walrus is not a sleek predator. It does not stalk or chase. But in this environment, it is a force that reshapes everything around it. At first, a walrus underwater does not look dangerous. Its movement is deliberate, almost lazy, a massive body drifting through the cold with surprising ease. Thick skin folds ripple as it swims, and its bulk seems too heavy for stealth. That impression is a mistake. In the muted light beneath the ice, scale becomes deceptive. A walrus can approach from below without warning, its dark shape blending into the deeper blue until it is suddenly there, rising like a living tank through the water column. This under-ice ascent is one of the walrus's most imposing behaviors. Using powerful fore-flippers and a dense, buoyant body, it can surge upward with startling speed, breaking the surface in a violent explosion of ice shards and spray. For anything resting or feeding near the ice edge, this emergence is overwhelming. The walrus does not need to bite to assert dominance. Its size alone clears space. Despite its fearsome appearance, the walrus is not a classic predator. Its diet consists primarily of benthic invertebrates, especially clams buried beneath soft sediments on the seafloor. To access this food, the walrus employs one of the most unusual feeding methods in the marine world, a technique that is both efficient and strangely elegant given the animal's bulk. A feeding walrus descends to the bottom, guided by sensitive whiskers that fan out across the sediment like a living sensor array. These vibrissae are densely packed and highly responsive, capable of detecting subtle differences in texture and shape. As the walrus sweeps its snout across the seafloor, it identifies buried clams not by sight, but by feel, mapping the hidden world beneath the mud with precision. Once a clam is located, the walrus does not crush it with its tusks, as many assume. Instead, it uses suction. Powerful muscles retract the tongue, creating a strong vacuum inside the mouth. This suction pulls the clam from its shell or extracts the soft body directly, leaving the empty shell behind in the sediment. The process is rapid and repeatable, allowing a single walrus to consume thousands of clams in a single feeding session. This feeding strategy has significant ecological consequences. By disturbing sediments and selectively removing clams, walruses influence nutrient cycling on the seafloor. Their foraging aerates sediments, redistributes organic matter, and alters the composition of benthic communities. In this way, the walrus acts as an ecosystem engineer, reshaping habitats without ever appearing to hunt. Yet to label the walrus as harmless would be dangerously misleading. The same adaptations that make it an efficient feeder make it a formidable opponent when threatened. Thick skin, layered with blubber, provides both insulation and armor. Beneath that, dense muscle and bone support a body capable of sudden, violent movement. And then, there are the tusks. Walrus tusks are elongated canine teeth that grow continuously throughout life. They are tools, weapons, and symbols all at once. Used to haul the body onto ice to anchor against currents and to defend against predators, tusks also play a central role in social dominance. In walrus society, size matters, and tusks advertise it clearly. At haul-outs, where hundreds or even thousands of walruses gather on ice or land, social order is enforced through intimidation and conflict. Bulls jostle for position, raising their massive heads and displaying tusks in ritualized confrontations that can escalate quickly. When fights occur, they are brutal. Tusks slash thick hides. Blood stains ice. The violence is not constant, but it is real, and it establishes a hierarchy that determines access to space, mates, and safety. This aggression is not mindless. It is structured and contextual. Most confrontations end before serious injury occurs, resolved through displays of size and strength. But when dominance is challenged repeatedly or space becomes limited, the walrus does not hesitate to escalate. In these moments, the animal's latent power becomes undeniable. Predators understand this. Polar bears, the primary natural threat to walruses, approach cautiously. A full-grown walrus is a dangerous target, capable of inflicting fatal injuries with tusks alone. Bears preferentially target calves or isolated individuals, avoiding confrontations with large groups. Even then, attacks are risky. A walrus defending itself or its young can turn the tables quickly. This dynamic shapes behavior on both sides. Walruses cluster tightly at haulouts, reducing the chance of individual predation. They position themselves near water, allowing rapid escape if threatened. Bears, in turn, probe for weakness, testing edges and waiting for mistakes. The ice edge becomes a chessboard where mass and patience compete. Underwater, the walrus's presence alters behavior even without direct interaction. Fish and other marine animals give way instinctively, sensing pressure waves and the looming silhouette of an animal too large to challenge. The walrus does not need to pursue them. Its movement alone is enough to clear space. Thermoregulation is another layer of this story. Walruses are built to survive extreme cold, with thick blubber that insulates against frigid water and icy air. But this insulation comes at a cost. On land or ice, overheating becomes a risk, especially during exertion or in warmer conditions. To manage this, walruses rely on behavioral adaptations, spreading flippers to release heat, resting in water to cool down, and timing activity to avoid peak stress. These constraints influence social dynamics. Dense haulouts increase competition and aggression, but also provide warmth and safety. Individuals must balance proximity against comfort, dominance against tolerance. The result is a constantly shifting social landscape, punctuated by moments of violence and long stretches of uneasy coexistence. From a distance, a walrus colony can look almost peaceful. Massive bodies lie pressed together, eyes closed, tusks resting on neighbors' backs. But this calm is deceptive. Every individual is aware of its position, its neighbors, and potential threats. The line between rest and conflict is thin. The ice edge itself amplifies this tension. As sea ice forms and melts, available haul-out space changes, concentrating walruses into smaller areas or forcing them onto land. These shifts increase stress, intensify competition, and alter feeding patterns. The walrus's life is tied intimately to the presence and stability of ice, making it a powerful indicator of environmental change. Visually, few sights are as imposing as a walrus rising through blue under ice light. Its bulk fills the frame, tusks extending forward, eyes small but alert. Light ripples across scarred skin, each mark a record of past conflicts and survival. It does not need to charge or attack to command attention. Its mere presence is enough. The walrus represents a different kind of danger in the marine world. It is not a hunter that stalks you, but a force you must account for. It dominates space, reshapes environments, and enforces boundaries through mass and aggression when necessary. To ignore it is to misunderstand the ecosystem it inhabits. In a world of sleek predators and elegant hunters, the walrus stands apart. Heavy, armored, methodical. It feeds quietly on clams, engineers the seafloor, and erupts into violence only when provoked or challenged. Beneath the ice, it moves with authority earned not through speed or stealth, but through overwhelming physical presence. The walrus is a reminder that danger in nature does not always come from teeth in pursuit. Sometimes it comes from something massive rising beneath you, displacing water, ice, and certainty all at once.